So thermoplastics. And so what is in here is four additional methods of manufacturing. You have extrusion and you have injection molding processes and other special techniques. The cool thing about processing polymers in general is that polymers provide the ability of being deformed quite significantly because polymers are quite malleable, and because of that reason, you can actually produce very little waste in a manufacturing process. And so in today's lecture, you will see how we deal with shape processes for plastics. You've seen how we deal with shaping of metals. Shaping for metals entails using drills and other techniques to shape the part, and we learned that already, but those processes do produce waste. While with polymers, you will see that there's ways to improve productivity, efficiency, and achieve net shape is the ability of achieving the desired shape with very little waste. So here are some examples of plastic products that are possible to do. Plastic can be shaped in a variety of ways. You have molded parts, you have extruded sections, and you will see, sorry, still dealing with it, films, sheets, insulation coatings, electrical wires, and then fibers for textiles. So different approaches can be developed, and here you can see some of the images for that. In addition, what you will see is that plastics are often the principal ingredient in a lot of different materials, like paint and varnishes. You will see that there. Adhesives. You'll also see that the plastics are also used in polymer matrix composites, and many plastic shaping processes can be adapted to produce a lot of different items. There are metal rubbers and polymers. So what are the trends in polymer processing? The reality is that the use of plastic materials has increased at a greater rate than any time in history. In fact, we're using that at least for the past 50 to 60 years, and the use of polymers because they're cheaper, and in many cases, as you learned from the previous lecture, polymers, you learn that we can actually create synthetic polymers. Because of that, the cost can be reduced quite significantly. You don't have to rely on natural polymers from the environment. You can instead synthetically create them, which allows you to then be very effective as a good replacement to metals. Although, if you're looking for the strength performance, you may not be able to get there for polymers. Plastic containers have been a large substitute for glass bottles and jars. You have seen that already in society, and the total volume of polymers is quite a bit greater than that of metals. And you may think, well, where? Well, let me give you an example. Look at a high performance bike is going to use polymers. Is going to use polymers in the way of composite materials, because composite materials are materials where you have fibers and they have a polymer epoxy that is going to help you deliver the loading environments required. Now, when I look at plastics, plastic shaping processes are quite important. It's probably one of the most incredible things that we can do with plastics. You can get almost any variety of part geometries. And by the way, now we're looking at new approaches using 3D printing to create possible geometries that were not possible before. Looking at plastic molding is a net shape process because you don't need to do additional refinements. Any further shaping may not be required. Also, the amount of energy required to do the shaping process is a lot less than that for metals because the temperatures that you need for the shaping process are fairly low. And the reason is because polymers at slightly higher temperatures than 100 degrees, in a couple of hundred degrees, you can already start being able to soften the material to shape it into what you need. When you look at metals, however, you're looking at getting to high temperatures, very high temperatures, excess of 500 degrees, to then being able to achieve something with them. And so for that reason, the energy required is quite low. And also the other thing cool about polymers in general is that you don't have to do additional treatment on the surface, like putting painting or plating may not be required. In some cases, it's very nice to have that. For example, in manufacturing, if I have a part that's critical for flight conditions, for example, and it's polymeric, perhaps painting in white is very helpful because the white paint will become an indicator of something that may have touched it and may have damaged it. So sometimes paint is used as a protective measure to give you an indication of a problem that may have occurred. Polymer melts is one of the things I'll talk about now. So to shape a thermoplastic polymer, you have to heat up the polymer. And the reason you have to do that is so it'll soften and so it can have that viscous behavior that's similar to a liquid. So in that form, these kind of thermoplastic polymers are called polymer melt. And important properties of polymer melt is the viscoelastic behavior of these materials, but also the viscosity, because those two properties allow you to shape the materials more effectively. Let's look at the viscosity of polymer melts. So what is the viscosity of polymer melts? It's a fluid property that relates shear stress to shear rate during flow. So think about a very rubbery substance that when you increase the amount of heat, the polymer material behaves a lot softer. So it's going to be a lot easier to shear the material because it's softer. And that's related to the shear rate, which is also related to flow. So something that is a polymer at temperatures will be a lot easier to deform, especially under shear deformation. Due to the high molecular weight, a polymer melt tends to be quite thick in consistency. It will have high viscosity. So therefore, most polymer processes, shape processes, involve flow through a small channel or die opening. I'll show you some examples with images. So these flow rates need to be often large in rates. And the reason is because you want to increase the high shear rate and high shear stresses. So that the significant pressure that's introduced will allow you to process and shape these materials. So yeah, you need the flow rate there, a consistent flow rate, so you can push the material through because it has high viscosity. Remember, it's not the consistency of water, but it's the consistency of, think of very thick paint that has been dried for a while. So think of that consistency. And by the way, if you never painted, I encourage you to go to Home Depot, get a little sample, and kind of play with it, right? So you can kind of understand what I'm saying. So let's study the viscosity and shear rate. So in the y-axis, you can see the shear stress. On the x-axis, you can see the rate of shear strain. So let me give you an example of where you see that in a common time frame. Viscosity of a polymer melt will decrease. So the viscosity will decrease with shear rate. So the fluid becomes thinner at higher shear rates. An example, you probably have all experiences. Toothpaste. When you're trying to push toothpaste, if you push it very fast, very quick, you're going to see a different behavior if you're trying to push it softly. You're going to see a different behavior in the way the material is coming out. But I don't know if you notice what's really happening there. The material is getting extruded from the toothpaste tube through something we call shear mechanism. And you know it's shear because there's a little, tube that comes out of paste and it's coming out extruded from something thicker. So that can only happen through shear, right? That can only happen through shear. That's a great example for that. If you ever play with putty, right? Kids play with putty. Maybe as adults, we should buy some putty so you can see what that looks like again for you. But putty material, also, when you play with it, you will see that the behavior for deforming those at high speeds when you play with it or softer speeds is different. So what you see here is the higher the rate of shear, the higher is the shear stress introduced. And then you have different kinds of levels. You have shear thickening, you have Newtonian fluids, your shear thinning, and then we have something called Bingham plastic deformation. So in general, the bottom line I want to point out here is that viscosity is related to shear rate, and the behavior can be used to our advantage in the manufacturing process. Now let's look at viscosity and temperature, how viscosity changes with temperature. In the y-axis, I have viscosity, and in the x-axis, I have temperature. And what you see here is that viscosity decreases as the temperature goes higher. So, in other words, the fluid is becoming thinner at higher temperatures, allowing us to be able to more easily shape these materials. So these plots that you see here are as a function of temperature for few polymers like nylon, acrylic, polypropylene, low density polyethylene, and those are provided for a particular shear rate of 10 to the 3 sec per second. And so what you notice here is a nylon and acrylic and all these different materials, the way their behaviors are with temperature are quite different. And polyethylene, you can see, has a lower viscosity than, for example, nylon or acrylic. So this was viscosity, right? So this viscosity here that I was talking about. And I told you there's another property called viscoelasticity, which is what I'm going to cover now. So I'm covering the properties the polymers have that allows them to be so effective in a manufacturing process. So what is viscoelasticity? Viscoelasticity is a combination of viscosity and elasticity. So those are possessed both by polymer solids and polymer melts. An example of viscoelasticity in action is die swell in extrusion, and in this case is when a hot plastic expands when it exits the die opening. So in this case, we're taking advantage of the elasticity of these materials in the manufacturing process. So let's show you an example visually of a die swell. So you have the flow of polymer, this is your polymer, and this is your metallic die, could be metallic. In this case, I'll say it's metallic. And the cool thing about viscoelasticity, right, is that polymers seem to have memory in them. And that's because of the polymeric chains that are formed. Those tend to have some memory in the way they behave. So what happens when you push the flow of polymer through this die, which has a certain diameter? We're going to take advantage of that because as the material extrudes, which we call the extrudate, the material will remember, hey, listen, I'm not of this diameter. I'm actually a larger diameter. I remember that. So the material will then go through the extrusion process and slightly become larger in diameter. And that's because the manifestation of viscoelasticity in polymer melts, where you can see that behavior being manifested, where the material is increasing in size after it goes through a die, because it remembers the polymeric cross-linking that had occurred previously. The extrusion process is a compression process in which you're forcing the material to flow through a die orifice to provide long continuous product whose cross-sectional shape is determined by the shape of the orifice. I can take advantage and use different shapes for the orifice to get the shape that I really want for the polymer that's going to be used in practice. It's widely used in thermoplastics and elastomers to mass produce a lot of different materials. Let me give you some examples like tubing, pipes, hose, structural shapes of importance, sheet and film, continuous filaments, coated electrical wires. All these processes use extrusion and they're carried out as a continuous process. And then what you do is when the material comes out, which we call the extrudate, this material, you can now cut it to the lengths that you need. So that's really what's going on here. Now let's look at the extruder in this example. Here, I'm going to cover like some of the materials involved. Here you have the components I'll be going through. So here you have the hopper, we call it. You're going to have some plastic pellets and heaters. They're going to apply the heat. You're going to have the polymer melt, which is here in this color here. So here's the plastic pellets. And as I'm extruding this material through this tube, which is going to occur by similar to a drill, where I'm rotating this and the material is getting pushed through here by this. Think of this as a conveying belt. So this material is getting pushed, the voids are getting reduced. We call the center section here a screw, and that screw is acting to move the material along. This metal encasing is called barrel. This first section is called the feed section. I apologize. Then we have the compression section, and then we have the metering section. The material now will get pushed through here, This section is called the barrel, and the purpose of the barrel is to break apart the material a little bit further so that it's easier to then go through this section here. We call this the breaker plate. That's why I say break apart. Then the material goes here and then it gets extruded at some velocity. So there's typical velocity associated with that. So the die end of the extruder, that's where the progress is being made through the barrel. So through the barrel here, and then ultimately it makes it to the die zone. Before reaching the die, the melt passes through a screen pack. And that's the screen pack I was talking about here. These tends to be a series of wire meshes that are used, supported by a stiff plate. And what is a function of that? It filters out contaminants. That's one of the things it does. And any hard lumping that occurs, it breaks those apart, which is why I called it the breaker plate. Also, it builds pressure in the metering section, which is very nice because now when I'm pushing through that tube, which I call barrel, if you recall, it strengthens the flow of the cylinder melt and removes the memory through using circular motion. So when you look here, by pushing this material through with no rotation, the material will have some memory to try to return to the original diameter they went through before the die. But by applying a circular motion, what people have found is you're able to break through the memory a little bit. And that then results in a more effective shaping process. Now, there's other types of solid cross section you can have. So here you have an extrusion die for solid cross section. Again, I'm doing a cut here, but all the stuff to the left is going to look like this, like here. Well, all I'm trying to show you here is that you have your screen pack here to filter the material. The melt flow direction is coming this way. You have your barrel like I discussed before. This is your breaker plate to be able to break the material down so it's easier to then form. And then here's your converging die entrance. And in this case, the point I want to make is a die is being used. And that die is being used to create, in this case, a circular hole. And you can see the extrusion die looks like that. But as the material gets pushed out, what you see is a profile that looks just like this one here, a solid cross section. So you can have different kinds of extrusion solid profiles that give you a lot of different shapes. So like you can get round shapes, you can get square shapes, you can get doors and window moldings out of this. You can get automobile trims. You can get house siding, for example, like the one shown here, by using the extrusion process. So what about hollow shapes? Because hollow shape seems like it will be magic, right? To be able to get that shape. But it's similar process where you have that screen pack still, the barrel, the melt flow direction, you have your polymer melt, but now what you have is an air channel. And the air channel is right here. And then now what's going to happen is that you have this polymer melt going around here, around the circumference, and you're going to send that material in 3 different channels so that when it comes out, it looks like this right here coming out, for example, like section AA, for example, here. What about if I want to do extrusion die to coat a wire? So typically you now do very similar process as this, not very different from this. Let me show you the full picture. It's not very different from this. The main difference now is I'm going to feed it wire instead. So what I'll do is I'll bring the bare wire in. I'll draw partial vacuum out. And the reason you want to draw the vacuum out is so that when I put it on the polymer on top to coat it with, you're trying to reduce any voids between the wire itself and the coating, because if you have a void, then it's going to come apart. So that's why this vacuum is pulled out. We call them this core tube. And now the material now is flowed down these channels to then basically coat your wire through it. Why you may need coating of polymers? Because of insulation typically. You may have seen this many times, like this is plastic that is coating wires, for example. But yeah, it is used for insulation, electrical insulation. Now, what about sheets and film production processes? Very widely used. Using it for calendaring, for for all kinds of things. We use plastics that are thin. So in this process, it does go through a very specific process. So let me walk you through this. Very similar process as before. I'm doing the cut here to not show the rest of it, but the melt flow comes this way. and you're gonna have a manifold over here. And then you're gonna push it through. Now I'm gonna do a cut here, section AA. So look at this section AA. I'm gonna do a cut right here. And when you look at the cross section, what you see is you have a conical type shape in a very thin slit. So the material is getting pushed through there. And then if I do cross section BB, you'll see that this manifold looks smaller, and you also then extrude the material. Now you may ask me, why is it wider here than here? And the reason is because the volume of the material is coming here and needs to evenly distribute to the left and to the right. Otherwise, you're going to have material coming out non-uniformly. So this is designed in such a manner that there's more volume flow here compared to the sides in order to distribute the material properly. But at the end of the day, you have a die slit that allows you to then get that sheet coming out in a uniform manner. So this is called a slit die extrusion. And here you have another process for what we call blown film processes. You may have seen these to bag materials, for example. And in this case, you're going to have an extruder, very similar concepts. You're going to have your polymer material going through this thing here, which is like a mold almost. And you're going to have these rollers that guide that polymer as it gets extruded out in this manner. And then obviously you're going to push some air in to give it some shape. That's why it's called blown film process, because air is being pushed. You can see a picture here kind of showing that. Calendering, I think you have seen calendering, but in essence, you may have seen sheets rolled up like this. And so here what you're doing, you're going to push the material through a feedstock with two rollers, and you're going to have multiple rollers trying to press the material down to a particular thickness. The thinner you want to go, the more of these two rollers you're going to have. And as you push the material down, you're starting to create a smooth, glassy texture, and then it comes down, and then you can start creating your sheet stock that will then gets rolled for then to be able to put it out for the market. There's other things that we do with polymer. One is called spinning. So that's a term that we use for talking about fiber and filament production. So spinning is a holdover method that has been used back in the day. I don't know if you've gone to Michael's or any of the stores, but if you bought any yarn or fibers, you have seen that these natural fibers are kind of twisting around as a single yarn or thread. But spinning is still a method used today, and spinning is part of the process that we use for creating synthetic fibers, which is the extrusion of polymer melt or solution through a spinneret, and then drawing them and winding it on a bobbin. A spinneret will look like this. It will die into multiple holes like this, and there's three variations of that that's used in industry. The first one is called the melt spinning, the second one is called the dry spinning, and the third one is called the wet spinning. So one is melt, second dry, third wet. So the melt spinning process, what you're going to have is very similar to what we had before, but there's a difference now. And the difference is you still start with the feed hopper like I had before. You're going to have your polymer granules here like I had before. Let me show you the previous picture to remind you. So this is a picture I had shown you with the plastic pellets and the hopper. That's your feeding there. Very similarly, you're looking at this too. Then you're going to have your heating unit. You create your polymer melt here. You have your pump, and then you have your spinneret that's going to look a lot like this here. And then now you're going to start getting the polymer melt flowing through that spinneret. And as it's going through that, you start to get solidification process, because what you're going to do, you're going to have air cooling applied there. And as that's happening, you're also going to apply some steam and moisture, because for certain applications you may want to have that. And all these things come together into a single yarn that now is getting rolled into this feed, and then you create your bobbin. So very similar processes as what you may have seen to manufacture yarns is used here as well. Now, injection molding is one of my favorite ones that are used in industry for creating plastics. They're polymer based. Polymer is heated in this case to a highly plastic state and forced to flow under high pressure into mold cavity. And in this case, it will solidify, and then the molding will be removed, and you get your part. So injection molding, very common, is produced to use a lot of components, part components even. Typical cycle time in the manufacturing process, 10 to 30 seconds. The cycles of 1 minute or more are not uncommon. You can mold a lot of different shapes, may contain a lot of different cavities. So injection molding parts also can be done to create very complex parts. We've seen this in industry quite a bit. There are some shape limitations, and it does depend on the kind of cavities you can create and molding you can create. Shape must allow to, you want the shape to be such a way that the part can be removed from the mold. Because if you can, then what is the point of using injection molding? The part size for typically that you're looking at here is 50 grams all the way up to 25 kilograms. So, for example, automobile bumpers. By the way, automobile bumpers are not there to protect you in a car accident. The plastic that's outside is a feature, but what's really protecting you is the reinforcements behind them. So these automotive bumpers are manufactured using injection molded parts. And the reason these are great is because they are quite inexpensive, economical, and number two, you can produce them at very high rates. And the cost of the mold is not as bad. So polymers for injection molding is the most widely used will be for thermoplastics in general. Some thermosets and elastomers are injection molded. We have seen that in industry, but you do require quite a bit of modifications to the equipment to make those work. And the reason you have to make those modifications to avoid causing the polymers to cross-link too early or prematurely before the injection process occurs. So that's why you have to make modifications to keep things fluid, because if they start to create links, polymeric links, then the molding process will be a lot harder. So widely used for molding thermoplastics, less common for thermosets and elastomers, but it doesn't matter that it's not done. It's done, but it does require modifications because those materials, thermosets, as you learned already from my polymer lecture, those materials are very hard. Once they harden, it's very hard to bring them back to a state where you can actually mold them to what you want. That was covered in the previous lecture. Here, what you can see is an injection molding machine. Has two principal components in these machines, an injection unit and the clamping unit. This is a picture from a photo courtesy of Cincinnati Miracle. So here's a diagram of an injection molding machine, and it's a very similar process of what I showed before. You have your feed hopper, you have your heaters, just like before. Very similar things going on here. I have not shown a picture of the left side, which has a cylinder that screws the material in. Is a reciprocating screw type that's used here. So that's very similar to what I showed before. There's animation there in www.vimeo.com that you can check out later. But the material gets pushed through this screw, and then when it gets here, you're injecting the material into this mold. That's the key here. That's the difference between what I showed you before, where I was pushing the material through this breaker plate and then through the die. Now what I'm doing, I'm pushing the material into a cavity that's your mold here. And then on top of that, you have this hydraulic cylinder with tie rods that push this movable pattern into this mold. It pushes it to be able to form the shape that you want. So the right side is pushing and pinching, the left side is pushing the material, the polymer material is being pushed, while the right side is pushing the pattern in to be able to create the mold needed. So the injection molding cycle here, what you see here is that the polymer melt is getting pushed into this cavity here, and then this movable pattern is moving towards the left to create that shape. And then here you can see more steps where the velocity is being applied to cause, because here you can see that the polymer melt has not filled out this cavity, but in the next step, as the velocity and the forces are applied to the polymer melt, it starts to flow into this material at the same time the mold is getting pushed to the left. And here you can see that the screw now, this screw will get retracted, and then the solidification part will now start occurring through the cooling process. And now this pattern, I believe, will be shown to be moved. You can see here, I move it to the right, Now the part is ready to be used. We call this mold is opened. The part is ejected, is what we call it. The part has been ejected from the manufacturing process. And in a lot of cases, you don't have to do more because this process is so efficient that it produces nearly net shape products. There's another technique that's used significantly in the composites community, but also plastic community. And these specifically used quite a bit on thermoset plastics. If you recall, thermoset plastics are very hard to bring them back to the original state. They're not like thermoplastics where you can melt them to then redo something new. This is also used for rubber tires and polymer matrix composite parts. So what you do here is you have your thermosets here, your particulates, you have your cavity here. This is called the punch right here. And the upper mold of the half is brought down against the lower mold of the half. We call this knockout pin. Here the charge is loaded. You then push this down like this, and now you have a compressed and cured process that's applied. You can cure it by applying temperature. In some cases, you can apply vacuum to remove any air bubbles. Then once you're done, this part is removed. This upper mold half is removed, leaving you behind the molded part. You may have heard of resin transfer molding. Very similar idea to transfer molding. In this case, the charge will be loaded into a chamber immediately ahead of the mold cavity. Here, it was provided directly. Here, you're injecting it through this charge. And so that's how this one works. You're pushing the material through, and part A here is pot transfer molding. Charge is loaded into a pot first. Then the polymer is processed through a curing process that usually requires heat, and in a lot of cases, vacuum to remove any bubbles again, and then the part is ejected. So very similar to this one, they're different, but this one is very good for thermosets, and then both of these are very good for thermosets. You also have one called the blow molding. Blow molding process is a process in which air pressure is used to inflate a soft plastic into a mold cavity. So now what I'm doing now is using air to my advantage. So that's important because you can make hollow plastic parts that you could not make any other way, such as bottles. So bottles are made this way because with bottles, you can now use air pressure to inflate the soft plastic into a mold cavity, allowing you to create a bottle, for example. A lot of consumer beverages are made this way, and you can make very high quantities doing that. There's another technique called thermoforming. So in this case, you have a flat thermoplastic sheet or film that's heated and they form into desired shape using a mold. The way to apply heating for these kinds of processes is to use like electrical heaters. And those electrical heaters are transferring heat through radiation into the part. And it can be actually applied to one side of the plastic or both sides of the plastic. This is used quite a bit in industry, by the way, to create like bathtubs, for example. That has been used for, like, if you look at the refrigerator, when you open a refrigerator, the plastic liners of that refrigerator are made with this, and the contour skylights, for example. So here is an example of vacuum thermoforming. Here, and I'll show the steps again, but here you have your vacuum holes. Here's your plastic sheet that you want to actually form. Here's your mold cavity here. And again, you need vacuum to remove any bubbles. This is your radiant heater here that's providing the heat. And here you have clamps that are holding the material together. Now what I'll do, I'll bring this piece downwards as such. The softened sheet is then placed over the mold cavity in this manner. So I'm just bringing this down here to this step. And then I'll apply vacuum here at the bottom, and that vacuum is going to pull that sheet down. You can see here this hole. I apply vacuum, this sheet gets pulled down into the mold, then being able to create the part by then removing the vacuum, removing the pieces apart, and you get your molded part. And this is one way that bathtubs are created. Applications of thermoforming, I already talked about it, but here are some more examples. Like if you've seen medicine packs like this, that's how they will do some of those. If you've seen, like, for example, meat products, those plastics are created in this manner. And then You may have seen this in shower stalls, bathtubs, certain toys could have this. Yeah. What about polymer foam? Polymer foam can be created by using, so I think everybody has dealt with polymer foam. If you've seen cups like metal foam, for example, you may have heard of polyester or styrofoam. If you heard of styrofoam, that's a trademark. Polyester is the right name for it. And then you have polyurethane. Other polymers, just a second here. Okay, good news. I have battery power. Okay, polymer foam. In this case, you've heard of these polymer foams. Other polymers that you may have heard of is natural rubber and polyvinyl chloride, PVC, you may have heard of. So polymer and gas mixture is used, and that gives it that cellular structure. That these materials tend to be very light because they are filled with gas pores inside. So there's two types that you may see in industry. One is a closed cell foam, and another one will be an open cell foam. But there's two kinds that you may see. And by the way, one type of material that if you wanna find out online will be Roja cell foam or dividend cell foam. Some of those foams are used in surfboards between the fiberglass face sheets, for example. And those foams tend to be closed cell foams. The properties of foam polymers, what makes this so special and so useful is that you can use them like in a sandwich structure to give a lot of bending performance. You can use them also in many places. Like you've heard of how PVC is used. Or low density, they also have a high strength per unit weight, very good thermal insulation. And the reason they have great thermal insulation is because of these gas pores. It's very hard to conduct through a material that has interruption of that material. And I have interrupted gas pores here that do not allow for the conduction to be as effective. So that's why they have great thermal insulation. Good energy absorbing capabilities. These gas pores also act as shock absorbers, allowing these materials to be used also for high impact applications. There's classification of polymer foams. There's three kinds that we use. One is called elastomeric, which is a matrix polymer, which tends to be a rubber, and it is capable of large elastic deformation. Another one that you may have heard is flexible, which is PVC, a soft PVC. And then rigid, which will be like polyester, or a thermoset like phenolic. A lot of application for that, I think you've heard of thermopedic pillows. You may have seen these water coolers use foam because they're great insulators. You may have seen them in cushion materials like furniture and bedding. Also, you may have seen them in packaging material and automobile dashboards. Like I'm not suggesting you should do this, but if you have a very old car, you may have seen cracks in the dashboard. And if you look in there, you will see it's made of these foam type materials. Also, you can see these are used a lot for buoyancy, like life-saving devices, lifeguard devices. And why? Because of the gas pores. Not only they're lightweight, they also float very easily compared to water, providing great characteristics for that. So how you deal with manufacturing, extrusion is one approach. So polystyrene is a thermoplastic polymer. You can use a chemical blowing agent typically that's fed into polymer melt near the die, and then the extrudate consists of the expanded polymer. Well, you can make large sheets, boards, a lot of different things can be made, like even heat insulator panels for houses. The shaping of polyurethane foams, here's an example here at the bottom. You can apply those by using spraying or pouring. That's one of the approaches that people use. It tends to be done in a one-step process where you have two liquids ingredients and you're mixing them together immediately to form a mold or any other shape. But in this case, the polymer is synthesized and the part geometry is created at the same time. You're getting both at the same time. You're spraying into a mold, you're getting that shape right away. And that's how we deal with polyurethane foam. Well, with that said, I want to thank you for your attention today. Very short lecture here, but I hope that you had a learning experience today. And